Hi everyone, Mrs. Basega here, and today we're looking at the final review for 5470 in the magnetism unit. You know I've said it a few times, so I'm going to say it another time. I'd like you to try these problems on your own first, then come watch this video to look at it, to check your work. Try it yourself first. Don't just copy down what I'm doing. Otherwise, you're kind of cheating yourself out of the practice. All right, so let's get to it. Question one is a picture of the domains in a ferromagnet. Domains are these little tiny sections of ferromagnets in which electrons are spinning, and those spins all happen to line up. So actually, if I even zoomed in farther on each domain, I'd have little spinning electrons, and those electrons are aligned with each other, and we call these things domains. So there's not really currents per se, but there are moving electrons. In this, the domains point from south to north. That means C would be a north pole, meaning A should be a south pole. Keeping on that pattern, domains are going to be aligned, pointing from south to north. And even if your magnet is dropped or broken in half for some reason, the domains will stay aligned, provided you don't do something weird like also heat it up at the same time. Since the domains remain aligned, this new magnet would have a south pole right here, because domains are pointing away from that area. And this new magnet would have a north pole right here, because the domains are pointing towards it. When this magnet is broken in half, it makes two ferromagnets. Doesn't make zero ferromagnets, there's definitely two, but each has their own set of north and south poles. Because one side is south and one side is north, these will attract each other. We can't really calculate, or at least you and I can't really calculate the strength of a ferromagnetic field, but I could tell from a field diagram because it would be the area in which the field lines are densest. D has the densest field lines, because if I drew an equally sized box around the letter C, it would only have one field line. B would have zero field lines. A would have zero field lines. So D has the greatest magnitude, that is, size of magnetic field. This is a picture of a battery. It's actually two batteries connected to a solenoid. This is an example of an electromagnet. If you want to be specific, it's a solenoid electromagnet. These are better than just a general ferromagnet like on page 1, because a general ferromagnet is not adjustable. An electromagnet is. I could make the field stronger or weaker. I could make the field switch directions. I could even turn the field off entirely. If this current went to zero, like because there was an open switch or something, then the domains inside this core would just go back to being randomly aligned all over the place, and the net field would go to zero. These also have the advantage of also tending to be smaller. The speakers inside your earbuds, those are actually electromagnets. They can be very small because you don't need a big core if some of your field is coming from these wires. In fact, the field is coming from these wires. Let's say it's going from positive to negative. So this wire is going, current's going all the way up, going back behind here and looping back in. This conventional current is causing the domains to align, creating a north and south pole. Now, to help figure out the direction, we're going to do the right-hand rule, and you're going to forgive my horrible drawing here. When I do the right-hand rule for the relationship of field and current, I'm going to point my fingers in the direction of field. So imagine I'm holding on to something, and these are my four fingers. If I do that, my thumb points right. try this out on your own. It's kind of funky because it's hard for me to draw like a hand behind this solenoid. So sorry, that's a weird angle there, right? Wherever direction my thumb points is the North Pole. Whatever direction's left over has to be the South. So now, if I were to draw the field lines around it, this field would point away from north and towards south. Great. Now, there is an equation that goes along with this type of field, and I call this the four C's. The field depends on the core, the current, the coils, and compression. Compression is like if I took the length of this solenoid from here to here, I would want L to be small so the coils are close together, concentrating the field. But in any case, I'm not too worried about L because it's suggesting that I'm tripling N and doubling I. This would make the field 6 times larger than the original because 2 times 3 is 6. Be super careful here that you don't do 2 times 3, or be super careful here that you don't do 2 plus 3 because these are implied multiplication signs in the denominator. So I'd be doing 2 times 3, not 2 plus 3. Now, there are a ton of changes you could make in order to increase this thing's magnetic field. I could put in a stronger core. And by stronger, I mean more ferromagnetic. I could increase the current. And increasing current can happen in many, many ways. Increasing current, you could just say, I increase the current. But you could also alternatively say, increase the voltage of the batteries. You could say more batteries. You could say less resistance. And all of those things would increase current and thereby increase field. For N, you can say increase the number of coils. And for L, you can say take the coils and push coils closer together. So those are my 4 C's to make this electromagnet as strong as possible. I want the best core, current, coils, and I want them close together. So now I've got this current. I've got this current traveling into the page. This little I symbol over here was for current in case you missed that. X means into the page, whereas dot would have meant out of the page. This current is in a straight current carrying wire pointing into the page. It's the field that is going clockwise or counterclockwise, not the current. The magnetic field is traveling in some sort of circle around this wire. But I have to use the right-hand rule to determine whether this is going like clockwise or counterclockwise. So in this rule, make a thumbs up in your right hand. Point your thumb in the direction of current. Literally touch your thumb right here. Watch the direction the fingers on your right hand curl. The fingers on your right hand should be curling in the clockwise direction. So if you imagine like a 12 and a 1 on a clock, clocks go this way, clockwise. A and C are both going to have the same direction field. In fact, A's field would be strongly pointing down, but C's field would be just weakly pointing down. The direction will be the same, but the magnitude will be different. And the reason the magnitude will be different is the field of a straight current carrying wire depends on the distance r that it is away, that point C is away from the center of the wire. The farther away it is, the less fields there is. And since C is 3 times the distance of A, If it's 3 times farther, then I get 1/3 of the field. So same direction, but 1/3 field strength. If I simply change, like turn backwards the direction of current, I reverse it from X's to dots, I'm still going to get a circular shaped field. It's still going to obey the right-hand rule, but try this. Dot means out of the page. So make that right-hand rule with your right hand. Give me a thumbs up. Point that thumb towards your face. The dot symbol means out of the page or towards you, and your fingers curl in a counterclockwise direction. So this would have the same field strength, but in the opposite direction, going up instead of down, clockwise or counterclockwise instead of clockwise. In problem number 16, I've got a wire loop moving to the right. And that's actually important because when I take into account the height and width, these two distances, the height of this coil is the one that's perpendicular to the velocity. That's the value of L I'm going to use when I solve this problem in a moment. This width of 0.3 is not relevant to solving the problem. Only the height, the distance that is perpendicular to the velocity, is the thing that matters. So L in our equation will be 0.4 in just a moment. It says to calculate the voltage induced in the loop when pulled to the right while it is still in the field. So you may be tempted to do this N equals BLV equation. I called this thing the shortcut equation, but that's the trick, right? This is the shortcut equation that you can only use if the coil is exiting or entering the field. In fact, while it's within the field, it's still inside the magnetic field, the delta V is 0 volts. This is because the shortcut equation is only true while entering and exiting the field. While the coil is contained entirely within the field, that change in flux or that change in voltage is caused by the change in magnetic flux. While you're within the field, the flux doesn't change. And I can draw this out for you. Let's say our flux is our product of area of this rectangle and how much field it's going through. Well, one moment from now, this same size coil is going to be enclosing the same area in the same field. When we do that, delta flux is 0. There's no change in flux. And 0 times anything is 0. Hey, it's true while it's leaving the field. In fact, if I were making a graph of voltage versus time, it'd be nothing when the coil is outside of the field, some voltage as it enters, nothing within, and some voltage as it exits, with these being just in the opposite direction of each other. Since it doesn't say otherwise, I'm going to assume N that there's only one coil. The field is 6, the length of which is 0.4. Note that length is this length that's perpendicular to the velocity, and the speed is 2. This gets me an induced voltage in the loop of 4.8 volts. If I wanted to generate a larger voltage, let's see what I can change. I could change N, the number of coils. Let's say I could make more coils. I could change B, create a stronger permanent magnetic field. If I had bigger magnets making this magnetic field, then I could generate more voltage with it. I could increase L, make a larger coil. And finally, I can make it go faster. And this makes sense to me because, like, if you put more kinetic energy in, you get more electricity out. This is the model for a generator. A generator takes the kinetic energy, because there's this velocity, and turns it into voltage, electricity. Number 17 is about magnetic force. Magnetic force might seem deceptively easy to calculate, like I'm just taking current times length times field strength, giving me 12 newtons. However, this is deceptively easy because there's a direction rule that goes with it. Force has three vectors. Force itself is a vector, current is a vector, and field is a vector. And each one of these is going to correspond to one of the directions. The field points away from north and towards south. In this case, the field is pointing into the page. And the field must be mutually perpendicular to the other three vectors. So it has to be perpendicular to the current. In this case, the current is pointing into the page. So the current is in the Z direction into the page. The field is to the right, that's the X direction. And that must mean the force is mutually perpendicular. That limits the force to it's either up or down. Okay. To choose which one, I'm going to point my fingers in the direction of field. I'm going to remember fingers point in the direction of field because I have lots of fingers and there's like lots of field lines. I only have one thumb, and my thumb is going to point in the direction of current. Once I get my hand into this arrangement, my palm is facing this way, down towards the bottom of the page. So my answer for 17A is down for the example on the left. And I'm just going to repeat it for the example on the right. My field was going into the page. Field was using up the Z direction, so my answer can't be into or out of the page. The conventional current is going to the right. So my answer for force can neither be left nor right. It means the force could only be either up or down. And now that I've narrowed it down to two, I'm going to use the right hand rule. So make a high five shape with your right hand. No bends or twists or curls or anything. Point your fingers away from you towards the screen. In fact, if you want, tap your fingers to the little X's. Then rotate it so that your thumb is pointing right. When I do that, my palm is facing up towards the top of the page because these three things have to be perpendicular to each other. So my answer for 17A, the example on the right, is up. All right, folks, that's it for magnetism. Best of luck.